has an imaginary term. So I am recording. Don't make any more stupid comments than usual.
Why don't you record the other periods? I'm just curious because I feel like they're more behaved.
I go between the two of them and I take the better.
Okay.
Some days it's us, some days it's them.
Did you take us when we had our drawings? Our pack drawings?
No.
Oh,
You know if you watch the videos.
that's true. But I don't need to. I experienced them in class.
All right. So it's the number of the form A plus BI.
Watch them online.
It's the number of the form A plus BI, where A and B are both real numbers. So going back, that double R, both real numbers. So something where we've got, like,
That was a stupid comment.
What did he say? What did he say? What did he say?
What?
2 minus 3i. As an example, Aber, A-B-E-R.
Guys, we're already losing.
Kelsey, we're not getting picked. This would be so funny if you do pick us and we're just
I didn't record this morning, so this has to go up there. So 2 minus 3i.
Wait,
The
what?
A is the bit that we call the real component.
Is there supposed to be a comma after the A?
Yeah, A comma B, where A is a real number, B is a real number. B is what we call the imaginary component. So right now it's a little bit of definition. We've seen imaginary numbers. I'm going to rely back on Algebra 2, that you remember things from Algebra 2, where they were solutions of polynomials, so forth. So we've got the imaginary component. So we've got the real part, we've got the imaginary part. Any number comes up is a complex number. Anything, any number system actually comes into the realm of the complex numbers. So our whole system of numbers, everything's a complex number. Everything's a complex number. Now within that, we have our pure imaginary numbers. So our pure imaginary numbers, is if the A term is 0. So that happens when A is 0 and B does not equal 0. So we have something like 3i is a pure imaginary number when it's just the imaginary component, when it does not have a real component. So everything is a complex number. Pure imaginary numbers are a subset of those. We have our pure real numbers that we just refer to as our real numbers. So we have our real numbers. So we've got our real numbers. We denote the real numbers with that double R. We can denote the complex numbers with a double C. You'll sometimes see that a double C is complex numbers. Those sets, a group of numbers that are themselves something called a group, have a special name. A group is something that is closed under multiplication or closed under addition. So if we take any two real numbers and we add them together, we get another real number. If we take any two real numbers and we multiply them together, we get another real number. So when I say the word closed, this is a little bit of something called abstract algebra. Math majors will take it. Physicists will take it. Everybody else, leave it to them. Closed is you take two things and you combine them, you get something more of the same thing. If you take a Macintosh apple and you take a Granny Smith apple and you splice the two trees together, you get another apple.
Isn't that how they made Honeycrisp?
That's how they come up with new apple varieties, is they take another apple, and so you've got the genetic material from one apple and another apple, and you make a new kind of apple. If you take an orange tree and you splice it onto an apple tree, you get nothing. You get a dead tree. So apples would be a closed system. The numbers are closed system. So complex numbers, everything's a complex number. Now we can split that apart into real numbers. Now we know real numbers, anything. The real numbers can be split apart into rational numbers and irrational numbers. So irrational numbers like square root of 3, pi, so forth. Rational numbers, anything that's a fraction. And then those rational numbers can be further split down. If we look at all the positive, negative, whole numbers, we can further break things down, where we've got our integers. But we don't really need to worry about that right now. Just there's sets that are sets that are sets. So this is a really kind of encased Venn diagram of sorts. We know what a Venn diagram is.
Yes.
Those bubbles where you look at the circles. Well, here we've got everything is a complex number. Everything falls under the realm of the complex numbers. Now within that, we sometimes have pure imaginary numbers. We sometimes have the pure real numbers. Pure imaginary numbers is if just that I. So you've seen this before back in Algebra 2. When we talk about imaginary numbers, when we have that I term, just as a definition, what is I? That we defined that. That came out as being the square root of -1. So mathematicians early on just said square root of -1, we're just going to make that I. That is I. It gives us a way of working with it. Calling it imaginary is really kind of a bad name because it doesn't necessarily mean that it has no impact on the real world. Without imaginary numbers, your cell phones don't work. Kelsey would have no idea what to do with her life if imaginary numbers had no work. Cell phone. Who's using a cell phone right now?
I'm taking good notes.
We're good. So imaginary numbers, it's kind of a bad name.
You're taking your notebook out.
It's kind of a bad name in that it makes it seem like they're not important, but they are super important in physics and engineering and in life. All right, we've got the imaginary number comes up. It's the square root of -1. I is the square root of -1. If you talk to the English teachers, they say I am the square root of -1. It's more proper that way. We've got powers of I. So we're going to go through with some arithmetic. Powers of I. Now, I'm pretty certain you saw this last year, but we're going to quickly go through again. If we have I squared, that is -1 because we've got -1, the square root squared. How about if we have I cubed? That is the same thing as I squared times I. Well, that's -1 times I. That gets us -I. How about if we have I to the 4th? That is I squared -1 squared.
Are we gonna have a section
That
where
gets
we figure
one.
out what
Yeah.
it is?
When it's like I to the 52nd.
And then we can keep on going. But if we go on to I to the 5th, I to the 5th, well, that is I to the 4th times I. That's 1 times, so we get I. So we can take this idea, it is cyclical in nature. So it goes right back to the beginning. So if we take I to the 19th, oh, I can't. There are 4 elements in our cycle. Well, this is the same thing as I to the 16th times I to the 3. And I bring up I to the 16th. What's I to the 16th? That is I to the 4th to the 4th. That's 1 times I cubed. And I cubed is -I. So it comes out, if we find, this is something called modular arithmetic, where we don't actually care about anything, we care about the remainder. There's something called modular arithmetic. Maybe you'll see this if you take a computer science course. It's the same idea as time. If we take, and this is a side, if we take 7 and we add 8, what do we get? We get 3. You go, what? You're crazy. No. 7 o'clock in the morning. It's 7 o'clock in the morning. 8 hours later, what time is it? It's 3 o'clock in the afternoon. 7 o'clock plus 8 hours is 3 o'clock.
Well, no, that's if you're using non-linear.
So that's the way the clock works. That's the way the clock works. So if we use base 12 arithmetic, modular 12 arithmetic, once you get to 12, that's 0, and then you start up. We're doing the same thing with the powers of I. So we have this cycle. We have that cycle. Let's take another one. I to the 487th. What we're going to think about is 487 divided by 4, since there are 4 items in our cycle. What's the remainder? We don't actually care about the value, but what's the remainder? Nope, don't even use a calculator. I'm nervous. 4 goes into 4 how many times? What's left over? There's nothing left over. 8 divided by 4.
Oh, that's bad.
I got 121.7.
Let's just think with me. We've got 487. 487. How many times does 4 go into 4? What?
Once. I thought you were gonna say 8. I thought you were gonna say 8.
I'm pointing at the 4.
But it's kind of hard to tell. I want to. This is all gonna be recorded.
No, if this is your fallback, you're on your own. We want the remainder. 4 goes into 4 how many times? What's the remainder?
0.
Okay, so we don't care about that. 8 divided by 4.
2.
2, what's the remainder? Okay, good, 0. 7 divided by 4. 1, what's the remainder? Is 3. The remainder is 3. That means that I to the 487 is the same thing as I to the third. It's all about what's the remainder. I to the third is negative I.
So then it's just what I to the whatever the remainder is.
It's I to the remainder.
Would you ever have a remainder that's larger than 4?
Ah, would we ever have a remainder that's larger than 4?
Then you would just add
You
them
just do
all.
that again, right?
So what if our remainder is 5?
Then the remainder is 1.
Then our remainder is 1. There we go. So, can you ever have a remainder that's greater than 4? No, because we can take out another 4. There it goes. So, we've got this. Let's do one more. Pick me some numbers. 2, 300 and 300 and 0. 300 and 0, and then I heard a 4 at the end. Okay, we've got I to the 23,004
That probably works out perfectly.
without a calculator,
Oh.
without long division,
Goes into 4.
dividing by 4. We should know because this was maybe 3rd grade when you go rules of divisibility. Dividing by 4, you look at the last 2 digits.
Miss Helena, what'd you do?
Can you divide 4 by 4?
Yes.
What's the remainder?
0.
So this is the same thing as I to the 0.
So 1.
We get 1.
See, I know math.
There you go.
Well,
All right, so we've got that cycle.
so.
It's a 4-element cycle. I, 1, I, negative 1, negative I, 1. I, 1, I, 1. The middle 2 are negative. So just remember that so you can go through powers. All right, complex numbers. We've got a lot to go through. Complex numbers. Let's go complex arithmetic. And put your head down and take a nap. 2 plus 3i plus 4 minus I. We're going to add a pair of complex numbers. Anybody got it for us?
6 plus 2.
Oh, yeah.
Anybody have any real friends?
No.
Anybody have any imaginary friends? When you're hanging out, the real friends go together with the real friends. The imaginary friends go together with the imaginary friends. They do not combine. Other things, otherwise they're really complex. You've got some other problems besides what math can solve. So,
I feel like math could maybe solve one.
notice, real components combine with real components. So real components combine, imaginary components combine. It's just like my friends. They do not cross over. So we've got complex addition. We're going to add together the real components. We're going to add together the imaginary components. Hey, that's just like vectors when we added the horizontal and the vertical components. Horizontal, vertical. Horizontal, vertical. Just the same thing with vectors. Not dot product, because dot product kept combined everything into a scalar. So it was looking only at the magnitudes. How about if we subtract? Let's say we've got 4 plus I, this time minus 3 minus 5I. We're going to subtract instead. All right, so we need to just subtract, we need to distribute. Still, real components, imaginary components. What do we got?
1 plus 6i.
We have 1 plus 6I. How's that look? We have 4 minus 3 is 1. I minus negative 5I. That becomes I plus 5I. We get 6I. So it's just be careful with the distributive property. Be careful with the distributive property. Just like vectors. Subtracting vectors, well, combine the horizontal, combine the vertical. Real components with real components. Imaginary components with imaginary components. Boom, there we go. So we've got addition, we've got a subtraction. Do we know any other whatever things that we use to combine two numbers?
You could.
To any other operations?
Operations. That's okay.
All right, let's do multiplication.
I believed in you, Mr. Liston.
Let's do multiplication. 2 plus 3I. Let's say we've got 4 minus 5I. Multiplication.
Six minus 15.
6 minus.
No, 8 minus
8, yeah, dude. Don't make me sound dumb.
Hey, 2 times 4 is 8, Chris.
It is.
Oh my god, Dude, I don't have the class researcher is so bad about math. I just need to.
What if I give you x minus 2 times x plus 3?
X squared minus 6.
No, you have to foil it. Don't
Oh,
you?
that's right.
Oh wait, so we definitely got that.
X squared
Yeah,
plus
we both got it.
x
We both got it wrong, so we're
minus
both
6.
dumb. All right. Oh boy.
Okay.
You're gonna be scared when I told you where I get accepted.
Same, actually.
I know, right?
Go to Lehigh for engineering. Just kidding, I'm not doing
Exactly.
engineering. I'm not doing. I did get into Lehigh.
I could go to Purdue.
Congratulations. Congratulations. I had one kid that worked for me one summer that he got accepted. He was going to UConn for mechanical engineering, and oh, he was awful. Like he could barely multiply, and it was like, you're a mechanical engineer? Oh no! I think it took him like 7 years.
Really?
You know what? He still graduated though.
He did.
He was persistent, Mr. Lewis.
Well, when you take the same classes 3 times, hopefully you remember the questions and stuff.
But now you see why I want to take math over the summer.
Let's take a look at this. Distributive property.
You
Distributive
remember the
property.
answers.
The distributive property is what we need to be careful with here. 2 times 4. We've got 2 times negative 5i. 3i times 4. 3i
Yes.
times negative 5i. You should have done this last year.
Mr. Dickman made us
And
take a
15
quiz
I
every
squared.
day in the beginning of class
Yeah, I remember that.
until we could
So,
distribute correctly because my class couldn't distribute.
we've got 8
It's 24.
We couldn't
minus
factor.
2i. Oh, look at this! I squared! What is I squared?
Oh my gosh, -1.
That
It's actually positive.
is negative 1. So that turns this into plus 15. We've got a total of 33, 23. Yeah, it is.
Negative I.
23 plus 2i. So there's our final outcome. Distributive property. Don't miss the distributive property. Sometimes we might call this FOIL. First, outside, inside, last. Just distribute. So multiplication, we need to be careful. We need to distribute. All right. Do we do division?
Can we?
We can divide. Do we have time for division?
Yeah, we do.
1 divided by 2 plus I.
What's up, Evan?
we're going to write this as a plus bi form.
Why do they use that sign when we're little? Because, like, you never use it.
Because it's supposed to mean you put the top over the bottom. Right?
I know. There is a notation. I don't remember
it's
where
so
that
dumb
symbol
because
comes
it
from.
throws you off so much.
I
Like
don't
when you're a
remember.
little fifth grader and then like you go to sixth grade and they don't use it anymore. It's like, what? Same
do.
with the X.
No, I mean, you do
The
that
dot
as a
and the x actually mean two different things. With vectors, there is something called the dot product, and in vectors, there's something called the cross product. There's two different ways of multiplying vectors. So,
Why don't
1
we
divided by
cross
2 plus I, because we needed three-dimensional vectors. We didn't have the time
product?
for
No,
it.
we're not feeling that.
1 divided by 2 plus I.
Moving on.
Actually, great. You say the three-dimensional vectors?
Any idea?
1/2 plus.
Plus 1 over
Multiply
I.
by the
Reciprocal to get to the top. Like that's me.
I like that idea.
I like Katie's idea.
Don't
I
you,
like
do
Katie's.
the, don't you do the opposite? Like you have to go 2 minus I. Is that it?
We need to
You
multiply
reciprocal.
I already said
by what's called,
Say what I said a little louder.
it's not the reciprocal.
The opposite? No, what's the opposite?
Oh, I can't remember what it's called.
Oh, I remember this.
The complex conjugate. That's it, guys.
If we have a plus bi, the conjugate is a minus bi.
Oh, God.
So the conjugates are change the sign of the imaginary term. Back when you solved polynomials, if you had a solution that was 5 plus 3i, you also had the partner 5 minus 3i. Solutions to polynomials of real functions, real variables, always come in pairs, the conjugates. There's a geometric reason for this that we'll get to in a couple days. But if we're going to divide, we actually multiply by the complex conjugate. When we multiply by the complex conjugate, that's the difference of two squares. That's going to be 4 minus I squared. That's going to be 4 plus 1. That's going to get us 5. So these two you can distribute and verify. We get 2 minus I all over 5. So you get 2 over 5 minus I over 5. You can distribute and verify that, but that's what it comes up to be. To divide, we multiply by the complex conjugate. Stop it there because we're out of time.